Hello and welcome to this month's Hive Live. In this workshop, we'll talk about how Bayesian networks can be used for cybersecurity risk assessment. We'll start with how the industry, sorry about that. We'll start with how the industry does risk assessment, and then how we'll show you with spreadsheets how that's usually done, and then how you can transition from the spreadsheet-based risk assessment to a Bayesian network-based risk assessment. At the end, I'll give you a preview of a Bayesian network that we machine learned from Verizon data breach investigation report data and Varus data. Just getting situated here. Okay. So Hive Systems presented at the 9th annual Bayesian Lab conference in October of 2021. What we presented at Bayesian Lab was directed at people who use Bayesian networks and are already sold on them. But we brought, in that case, cybersecurity to the table. What we'll present today is geared towards cybersecurity and risk professionals, ages 10 to 90, that are new to Bayesian networks. And the Bayesian Lab conference is really just a group of people that's mostly researchers that are doing really fantastic research in areas including cybersecurity, using Bayesian networks. And Bayesian Lab is the name of the product that is from Bayesian, the company, who also leads that conference. So I'm going to go over this slide. I know some people who are familiar with this have seen it before, but just to get everybody on the same page, this is what we're taught to do for risk assessment and cybersecurity. Step one on the left side is of the spreadsheet. You list ways hackers can steal your data. Step two on the right side of the table, you rate each of those scenarios by how probable they are. You go through again, you put in estimates of what impact those scenarios have. Then at the end, you multiply the probability scores times the impact scores, you get your risk score. So there you have it, your risk has been assessed. Now pay for cybersecurity. That's usually how it goes. So basically it's a 5-star rating system, but then they multiply the stars together, which so far, not even dubious marketing firms have tried yet. So as an example, if you have a risk scenario that's malicious email attachments being used as part of a data breach, what's the probability of this for us, this company, over the next 12 months? I might say, I give it 2 stars, or a score of 2. Then what is the potential impact of an email originating data breach? I give it 4 stars because it might be 2 stars probable or 4 stars severity. Then the risk analyst multiplies those star ratings together, 2 times 4, 6 stars. So the risk of email-based data breaches is a 6-star risk, or a high risk. The magnitude of badness is multiplied by the probability of badness. This is what regulators have lowered their standards to because people have a hard time adopting anything more sophisticated than this. If you ask people to use dollar amounts, their management gets very nervous about having risk like that on paper so explicitly. There are a variety of other reasons. If you ask people to use percentages, people have radically different definitions of what 10% means compared to 20%. So the best that is recommended and that you have to memorize in order to get security industry certifications is this dubious scoring method. Your job as a security professional becomes lowering that score with your security expertise and your controls that you help organizations implement. When management is inevitably confused by these scores or stars, we're taught to present the risk with a traffic light colored heat map that dazzles management with pretty colors. And we say, fear not, my cybersecurity skills will move you from a high to a medium, from a red to a yellow. That methodology doesn't actually improve decision-making, even though it is by far the most popular. Subscribe to Hive Live and our ACT blog if you're interested in learning more about that. We have a series called On the Shoulders of Scientists, where we bring up the scientific research on those topics in particular. I'm going to start with this method because it is where most people are at once, and it's where I started as well. I'm going to explain how the spreadsheets that spreadsheet model of risk maps to a Bayesian network model of risk. And to do that, I'm going to first explain the basics of graphical network diagrams, one of which is a Bayesian network. So for whatever reason, humans like to think of things as objects in relationships. As a result, there are a lot of different things that use the structure of objects as nodes and relationships as lines in between them. That might be because we're social creatures, I don't know. Good PhD topic. Whatever the case, we've settled on circles and lines conceptually and visually to model and communicate the existence of things and how these things relate to each other. Bayesian networks use the same terminology that object relationship mental models and visualizations use. So the circles are called nodes, and the lines are called arcs or edges or links, depending on what discipline you're in or what software you're using. And you've seen this in its most basic form in places like workflow diagrams, computer network diagrams, or relational database diagrams in Bayesian networks. You've probably imagined something like this when you think about social networks. And what these have in common are these simple shapes connected by simple lines. And the lines are just lines, as opposed to arrows. They represent simply a relationship of some kind, any kind. You're only going so far as to say there is a relationship between these two things. I'm not saying if it's negative or positive, whatever. This diagram is meant to communicate that person A and person B are associated somehow. And depending on the purpose, that might be fine. This diagram shows a one-way relationship. But to clarify the direction of that relationship, an arrow is typically added. For those of us in cybersecurity risk, data flow diagrams made up of relationships like this one should be familiar. Computer A connects to server B. Normally, people back up their servers, so you add that into the visualization of your computer network. In real life, you also usually name these things instead of just having A and B. Social networks work the same way. You've got people who have relationships with other people, and the diagram models the people and the relationships between them. Oftentimes, node names are self-explanatory, so the people shapes aren't necessary, and you can drop those. And so now, as you can see, we're getting closer to what you maybe saw in screenshots of Bayesian networks. So this is a visualization of a network of things. In other words, a graphical network. Congratulations, you now know what a graphical network is. But what would a graphical network of a traditional risk spreadsheet look like? As the risk assessment guidance usually says something like, list your scenarios, list the probabilities of those, list the impact of those, multiply them together. And so that this is what ends up being the core of a lot of risk assessments. To help understand what a graphical model is, whenever you see a spreadsheet or a data set, try imagining your columns as your nodes in your network, and your formulas, like the ones you might make in Excel, starting with an equal sign, as the arcs, the lines in between the nodes, because they define a relationship between two or more cells. That ends up being how we define relationships in an Excel sheet or in a spreadsheet. And because a graph diagram essentially breaks apart those columns, you can also use arcs to define the non-mathematical relationships between nodes as well. So not a formula, but just to simply say, this node is a parent of this node, or this row, this column in your spreadsheet is a parent of this column in your spreadsheet. So this is your spreadsheet freed of its linear constraints that it normally has. The information is still the same. So the relationships between the columns are still the same. It's just a slightly different visual format. Scenarios influence the probability of that probability column. Different scenarios have different probabilities. So scenarios influence the impact column as well in the same way. You can have a network that draws a line directly from scenario to risk. So you'd have a simple 2-node graph or 2-column risk assessment. But think about the spreadsheet equivalent of what it would be like to actually do a risk assessment that way. That would be your spreadsheet, 2 columns, one for your risk scenario, one for your risk valuation or score. You could do that, but then you'd be taxing your brain with estimating the probability and the impact and how they interact with each other and the output and into one column, one cell, trying to do that all in your head. And that would be difficult, but also harder to prove to auditors that you've actually considered probability and impact behind the scenes. And you'll find that most of the standards say something like thou shalt consider the probability of a security event as well as the impact. Understandably, because there are lots of things in cybersecurity that are high impact, most of the stuff we talk about, but they're not necessarily probable. And we are always forced to pick based on those 2 factors, which security controls are worth implementing. So both of those factors, at least those 2 factors, probability and impact, are important to us, as well as in most areas of risk. At this point, you've made a pretty graph diagram representing a 1-for-1 equivalent of what your spreadsheet does. So let's take that a step further into Bayesian land. You notice that there are question marks in our cells because this is a model of the structure behind the traditional risk assessment. So every time the event or scenario under consideration changes, the values change. The values change. There we go. So suppose this is a risk assessment for a server being subject to a data breach, and your regulator says you need to use a simple formula of probability, score times impact score equals risk score. You estimate the probability of a breach as low, maybe because it's air-gapped. Then you estimate the impact is high because it's sensitive data, and that if it's breached, it's very costly. So the risk node or column has a formula in it that takes the probability value and multiplies it by the impact value. So the result is a risk of high. So those first 3 nodes are really just raw user inputs, and that last one has a formula in it, just like an Excel sheet. Because you only have 3 options, or maybe you have more than 3, more than high, medium, and low. So maybe you're saying very low, low, medium, high, very high, or something like. It doesn't matter. You're still cutting up reality into what you're really saying is that you've divided the infinitely complex reality into 3 discrete options, and you have to pick one. And you're only supposed to pick one for most of these models to represent your probability, and then pick a separate one to represent your impact. Maybe it's a low and a medium. You're probably taught in school to communicate probabilities in the form of percentages or proportions. And for some reason, we're not held to that standard in the professional world. So instead of thinking of probability like a 100-star rating system, so to speak, or even the 5-star rating system of commerce, we're asked to think of probability of events happening and impact in terms of a rating system. So what we're really saying with ordinal scores is that a probability of low is something that we expected to occur 0 to 33% of the time back in our grade school math terms. A probability of high is something we expect to occur 66 to 100% of the time. And a probability of medium is somewhere in between. There are lots of problems with this 3-bucket model, but again, subscribe to our ACT blog and our Hive Live to learn more about that. So if you make a node representing the probability in Bayesian Network software, in this case, I'm using Bayesian Lab, the Bayesian Network, which is a Bayesian Network studio software, it looks like this. So remember, each node is really just a column of a spreadsheet. It's almost like you're rotating and viewing the column from above. So you've got your high, medium, and low buckets as choices or drop-downs for those cells. And when you haven't made a choice of which rating is appropriate for your scenario yet, you're really saying that you have no idea. It could be any of the 3. And when you're ready to pick your estimate, you pick one. When you pick one, you're saying you're putting all 100 eggs into that basket. To say like this, when we do our 1 of 3 choices at risk assessments. And then let's talk about impact rating. With probability, we're taught a standard 0 to 100% scale, where 0 means never going to happen, 100 means definitely going to happen. Conveniently, there isn't anything above 100 or below 0. When it comes to impact, the possibilities of losing value are infinite. So we can lose $0, or we can lose 100, or we can lose 101, or 3 billion. When we apply words like high, medium, and low as a rating of the impact of an event, we have $0 as a nice solid floor, but we don't have a ceiling of how much money we can lose, how much this event can cost us. To put it like I did before for impact, a risk rating of low means losses from $0 to some dollar amount that you choose. A risk rating of high means losses from some dollar amount to infinity. And a risk rating of medium means somewhere in between those ranges. This can be problematic with decision making because if you draw your line for high risk at $100, then you're giving the same score to a $101 risk and a $1 billion risk because they're in that upper something to infinity bucket. Your model is still accurate, your computer is still behaving. It's just because high acknowledges some dollar amount to infinity, but the model at that point is uninformative and even dangerously misleading. But let's assume you're okay with that because maybe your department has some silent assumption that the highest risk ever is $1 million or the company's value or something finite. Like in your spreadsheet, you selected a probability rating, an impact rating, and you got a risk rating. But remember, the node on the right just has that formula, probability times impact, just like your spreadsheet cell did in this case and what's shown on screen. And then the dial is with the colors is just for visual satisfaction. I don't think it's all that useful, but a lot of people like that, dashboards. In my example, I had explained those risk scores with dollar amounts and percentages. So let's actually use dollar amounts and percentages in our nodes or columns instead of scores. That transition from risk scores to dollar amounts and percentages is where the industry is heading. And having a clear dollar amount gives us something less sensitive to varying subjective understandings of words like high, medium, and low. We all have different ideas of those words, but we all have a pretty clear idea of the value of money. So notice, though, that the issue still remains that a high consists of any risk with losses greater than 100,000 in this case. So in cybersecurity, the domain of potential losses varies extremely and oftentimes suddenly. So to have models that can't ride those waves is risky in itself. So if you review public data breach loss amounts, you'll find situations where massive sensitive data sets are breached and cost a company hundreds of thousands of dollars. But then you'll also see losses due to a single stolen laptop that an employee left in a cab that contains significantly less data about significantly fewer people. But the type of data in that spreadsheet is so much more sensitive and upsets the right people, so it ends up costing tens of millions of dollars in losses. For this reason, that bucketing or discretizing can be hazardous when assessing risk in our domain. All of those issues assume you have a fairly good idea, still assume that you have a fairly good idea of the potential losses. And then there's still this elephant in the room that is not represented with this methodology, even in a Bayesian network, and its name is uncertainty. So this approach still doesn't allow the expert to say, I'm really not sure about my choice in the high, medium, or low bucket. Fortunately, researchers have repeat success with the use of getting range estimates from experts. So you ask your expert to provide a ballpark and then estimate, and then have them narrow it down some, but not to a single number. So you keep a range of some kind. Basically, don't let the humans converge on a single number. Humans don't do that well. We can collect ranges for probability estimates as well as impact estimates, shown here. And so, for example, you have an engineer, or Amazon Cloud, if you're outsourcing, says the cost of replacing a particular server due to ransomware could be as little as $1,000 or as much as $100,000. But most likely, for most people, it ends up being around $4,000. That's a range estimate. Most of the time, the ballpark is all the resource managers are looking for. In America, the conversation usually sounds like, what are we talking here, $2,000? So just like how you would put scores into a Bayesian network, we can put ranges into one. And here's what one risk scenario model can look like as a Bayesian network, in this case, rendered in Bayesian Lab. You have your same setup, risk scenario on the left, probability estimate. In this case, it's a 3-point estimate. They said from 10 to 75% probability with a most likely of 30. After they saw it on screen, they might have said, nah, you know what? I feel more like it's coaxed to the lower end towards 0 or to the upper end of 100%. Same thing with the impact or magnitude estimate. Their ballpark was, it could cost you anywhere between 8,000 and 10 million, but most of the time it's 8 million if this malicious email attachment scenario were to occur. Then on the right, you have the aggregate of those things, or the product of those two things, where we were multiplying scores together. We're instead now multiplying distributions together, or the average of those distributions that you defined. So I've isolated a single risk scenario here, but what's great about Bayesian networks is that you can feed in those spreadsheets of risk estimates that you had before to populate this. They get an instant calculation of the risk as well as the spread of the uncertainty. You can also just put estimates directly into your Bayesian network, like click on, and you can just click on these and type in the estimate into the green nodes, and they call that parametric because you're entering your range as the parameters of a distribution. Bayesian networks can also handle range estimates like that. They can handle range estimates that are essentially non-parametric. So instead, you can have the person click and drag those little columns, in the blue columns in here, to be the shape of the probability density, the shape of where they think the most likely outcome is. Shown here is the user input approach, where I updated those green nodes by just double-clicking them, typing in that value with my estimate range, and most likely, either from what an expert said and or from an industry report, or maybe something your cyber insurance or an actuary was able to give you about your probability or impact. The distribution shapes, those bar charts, are the result of a probability table, which you can think of as just a little spreadsheet built into each of these nodes, getting populated by the parameters that you entered. So what you're saying is there's a blank spreadsheet inside of each of these little nodes, and you're saying, computer, make a video game where this bad thing happens 10 to 75% of the time, but typically 30% of the time, and it creates a fake or synthetic data set that fills in what you described. You have one such node for probability estimates. You have another for the impact estimates. They're working the same way in this case. Then, just like with spreadsheets, your risk column / node takes in the probability and impact values and combines them, factoring in both. But notice here that instead of simply multiplying scores together, we're multiplying distributions together, and we're keeping our uncertainty in the model, and it's driving our output responsibly. And the output risk and characterization of uncertainty distribution on the right is populated and visualized, also containing that uncertainty. But then if somebody does want a single value, they might use the average loss as calculated across that distribution. You'd repeat that process for each risk scenario, like in a traditional risk assessment. And the next step would be to propose security controls and then recollect those estimates with those security controls as conditions that reduce the risk. So you go through And the quick way to do it would be just to replace that risk scenario column with a little thing at the end that says plus or given. We have a firewall, we have antivirus, we have backups, etc. And then they would put in the new estimates. There are more sophisticated ways you can do that with a Bayesian network, but for this talk, just introducing to Bayesian networks, that does work. The only thing you lose by doing that is if you have a control that affects multiple scenarios in the same way, you don't have to keep repeating its estimate. You can just basically draw your arrows to those risk scenarios and say firewalls decrease risk the same amount, same way to all these things, if that's the case. And so that saves you a lot of time. So as you can see here, we're talking probabilities instead of simple selections to characterize the risk that is in our minds as security professionals. The value of a Bayesian network is that we're getting probabilistic statements of the risk instead of a single point score. We're capturing our uncertainty by saying the reality over the next 12 months could indeed play out as any of these within a ballpark, but that I suspect, given my expertise and our data, that it will be closer to this range of losses. And what's more, for us in cybersecurity is that Bayesian networks are mathematically formalized, so they're very easy to find in any programming language and so easily connected to hard data sources like your log management server, firewalls, honeypots, or threat intelligence feeds. So obviously you can do this with other methods like formulas and spreadsheets or simple Monte Carlo simulation. But by using a Bayesian network, you're making something more atomic and interoperable with other computational systems that use this brilliance in mathematics by people like Judea Pearl and colleagues to be efficient and programmatically elegant about it. In short, the interoperability with humans and machines and the efficiency for use at small and large scale is how I'd sum up the value of Bayesian networks. And to touch on just the fact we're using estimates, which a lot of people aren't comfortable with, understandably, if an expert is calibrated, their estimates can be reliable, especially if you're evaluating their performance at providing estimates. But if the expert is not calibrated and you decide just to use all the interns or something to provide your estimates, we've still externalized their mental model for peer scrutiny and ongoing refining. And if we don't want to use experts, we just plug a sensor or a computer with real probability impact or an idea of the probability and impact, because our sensors don't pick up on everything, but you can plug those directly into the nodes instead of having a human enter in the estimates. In the same ways you can imagine clicking equal sign in your spreadsheet and then going over to your log management tool and clicking on it and saying, just take in whatever comes from this. That is essentially what you're doing and what you're able to do with the Bayesian network. So Bayesian networks can accept human and machine inputs and also a combination of both. I talked a lot about estimates because that's the default approach for risk assessment in cybersecurity, but using data when done carefully can help you build even better models. The most common reference I've seen in cybersecurity when people are asked, what did you use to create these estimates? What kind of data were you able to look at? Some people can say, we have a lot of great internal data, but we also, or they might say, we look at the Verizon data breach investigations report. So I was thinking, or we were thinking, wouldn't it be nice if we could just ask the PDF of the Verizon data breach report to tell us what is our risk given our company size, our industry, et cetera. The data set behind the DBIR is not made public, unfortunately, in its entirety, but the summary statistics and distributions are. So I entered those into Bayesian Lab, along with the sample sizes as prior weights. And what that means is that I have a Bayesian network that assumes the reality of risk as communicated by the DBIR, but the strength of those estimates, of the probability estimates that will come out of this Bayesian network, are only as strong where they're weighted by the sample size that Verizon reports. So whenever you see something that's like an N of 5 and you get kind of nervous because you're like, well, that's only a sample size of 5. How can I trust that? We're factoring that in to the Bayesian network to say, don't trust that estimate so much. So on the left here in yellow are the stats about investigations that ended up in data breaches. And on the right in black are the stats about investigations in general, whether data breach or not. Subscribe and share and comment if you want to hear more about the DBIR Bayesian network we're working on. It gets a little bit into the weeds, so I don't want to go into it too much here. And I also wanted to show this. For fun, I did take the portion of the data that informs the Verizon report, which was based on a community source database called Varus, and companies that have security operations centers contribute to that, contribute their investigations using the Varus schema, where you take your security incidents and you categorize them and you record what happened in a particular format so that they're standardized, can go into this database and they're anonymized, and then everybody can learn like what do the attacks look like as they occur in organizations. And the features now go well beyond the basic security investigation, technical observables. They used to include just things like source dest IP port type of attack, if you recognize it. Now they include things like organization size, breach costs, realized at the end of the year or whatever, whether company policies were followed, etc. Here we picked just a few interesting variables. So remember, variables are columns. So we took a subset of the columns from the Varus database, which you can get as a spreadsheet, and then ran a variety of machine learning algorithms against them to identify what the relations are between the nodes and how strong they are. And this was just a quick unattended batch learning. So we didn't set the parameters as you should do when you use machine learning. This was just a quick exploration, but we're doing more pointed efforts to create a more interesting network. But if you just throw the Varus database into any software that has machine learning algorithms built into it, in this case, Bayesian Lab, you'll get something like this. And it does make sense. Bayesian Lab discovered the clusters and patterns quickly. It knows nothing about cybersecurity. It's just seeing how, as some columns increase or decrease, other columns can consistently increase or decrease. Maybe they're related to each other. And then it keeps kind of experimenting on that theory or hypothesis by going through the rest of the rows. And if it holds up, like, yeah, these two cells are definitely related, it keeps that as a relationship. It defines it here as a arc or line in between your nodes. With parameter updating, our security operations center could keep updating a network like this as they go about their day-to-day investigations. And by doing so, they might be able to get a reliable probability of whether their investigation is going in the right direction or not. So security controls like antivirus and firewalls reduce the probability of these kinds of events variables. So when we add nodes that represent security controls to networks like this, we can include that, and we can include the costs of those controls. And because we can include the costs, we can also run through many different kinds of control optimization choices to say, if you imagine a node that represents each of the security controls you're considering, you can say, if we switch on these nodes, the firewall, the antivirus, the XDR platform, whatever, what does it reduce, where, and how much? And that could be machine learned from data or defined explicitly by experts, or both. So I'm going to just zoom into this, some of this, and don't take this as like reproducible, because again, this is we just took the Varus data set, ran a batch script that did all the common machine learning algorithms used for Bayesian networks, And we've just picked the one that had basically the strongest confidence. So basically tried to draw those little arrows from each node toward every single other node based on the data. To think of it in a spreadsheet term, imagine you have a spreadsheet with lots of cell references and formulas and cells that you made. Now imagine that you've selected all the cells in that spreadsheet and then pasted them as values so that all the formulas are gone. You've like flattened out the data. It's just data, no formulas anymore, because you're done doing formulas. So all you're left with are these values that come out of those formulas. Now imagine challenging your computer to rebuild all those formulas just by looking at the values in the spreadsheet. So your computer tries all the different combinations of cells, multiplying and adding them together until it reverse engineers what formulas you had used to create that original spreadsheet. It was reverse engineering the formulas that you might have had to create those values. That's what's going on here. In this case, we're given a big data set of security investigation case notes, and we ask the computer to reverse engineer the mechanisms behind those. Security investigators weren't using formulas in a computational sense for their investigations, but there are patterns that are formulaic that the attackers might have used or that the network was prone to that can be reverse engineered. Machine learned Bayesian networks are beyond the scope of this talk, but please subscribe to show us you're interested, and we will dig into these. So thanks for taking the time to listen today. I hope it gets you excited about Bayesian networks. If the topic interests you, subscribe, share, comment. If you show interest, we deliver more content. We'll continue sharing these free videos and resources about Bayesian Lab, Bayesian networks, specifically how they can be used to solve cybersecurity problems. And you'll be able to find those here, Bright Talk, or hivesystems.io, YouTube. Follow us on LinkedIn or any of those to get notified when they come out. And let's get to some of these questions.